Okay. Uh, Hi, my name is Kai Clymer, and I am an instructor on a course on sustainability. And Dr. Qiao today has graciously agreed to talk about sustainable aviation. So thank you so much for coming.
Thank you. Thank you for the introduction. It's a pleasure to be here. I'm sure you, either in the room or online, that joined us today, hear about sustainability, right? So I've been always really passionate about this topic. In fact, in 2008, I developed a new course for sustainable energy solutions. I talk about fuel cells, hydrogen, and the alternative fuels, a lot of the topics that actually today we're going to review today. But we're going to focus on aviation. So I'm very glad to be here. I'm going to share with you my understanding about the path to sustainable aviation. So again, I am a professor in the School of Aeronautics and Astronautics, and my expertise is chemical propulsion. So for those rockets, gas turbine engines, energy, or any energy devices where we convert the chemical energy of fuels, propellants to useful work, that's what I study. Okay, so all right, let's take a look at this diagram. This one shows the number of passages carried over the years, from 1945 up to 2022. The blue curve is total passage, and then domestic, that means United States, which is the yellow curve over here. Now, obviously, you can see, let's just forget about the pandemic for a while. It's this kind of trajectory. It's not linear, it's exponential growth. And with all kinds of crises and wars that disrupted a little bit, but eventually, quickly recover, keep growing. And then here, this is really what we experienced in the last couple of years, COVID pandemic. There's a significant drop in air travel in aviation. But up to today, I'm pretty sure we have pretty much recovered, right? So the trend will be going up, just like this curve, this blue curve, we're going up. And then it's expected in the next decade or 2 decades, it's going to double, triple, or even 5 times the amount of passengers carried by airplanes. Now, next, I want to talk about what exactly the emissions from aviation. Currently we'll talk a lot about carbon dioxide because that's the global warming, that's the climate crisis we're dealing with. But carbon dioxide is not the only one. There are also nitrous gases. There's also water vapor, and there's soot, sulfate, particulates. So these are all kinds of emissions that from the exhaust of aircraft engine. Now, this is a study really focused on the effect of these chemical species on climate. They can either warm or cool the climate, either directly or indirectly. So the bottom bar, this colorful bar, basically just tells us, each of these species relative to CO2, their contribution to global warming. CO2 is 1, because that's a reference. Nitric gases and also ozone. And the methane actually is blue. That means methane cools the atmosphere. Sulfate also cools. So this is to give you an idea about, carbon dioxide is not the only pollution. There are others. For example, nitrous gases, NOx, ozone, those are the things really important, right? We have to deal with. The rest, like water vapor, is also a global warming gases, but we don't really truly care about water because this planet has more than 70% of water. These geoclimate mechanisms can regulate water. If you have too much water vapor in the atmosphere, rain, they're going to condense. So there's a mechanism. But carbon dioxide is more than 70–80% of all the emissions from aircraft. Their recycle time, if you emit a ton of carbon dioxide, they're going to stay in the atmosphere for maybe 100 years before it can be recycled. So this is why, from the climate perspective, the focus is really carbon dioxide. Now, next, I want to show you global CO2 emissions from aviation. Again, this is consistent with the number of passengers aircraft, airplanes carry that I showed you in the very beginning, right? It's going up. This is actually the red line is the total CO2 emission in 2018, which is about 1 billion tons. Now, aviation is about 3% of the total carbon dioxide emission. 3%. Okay. Again, it's going to be increasing maybe to 5% in 10 years and even more. Okay. So this is something that we cannot ignore. You have to address that if we want to achieve a net zero carbon future. All right. All right, next, let's start our journey to sustainable aviation. So again, I'm going to share with you my understandings of, the technologies in the future and what needs to be done in the future to achieve sustainable aviation. Now, the first question is, aviation perhaps is the hardest transport sector to decarbonize, right? I read a report by National Academy of Engineering. Basically, what it says is, in order to achieve a zero carbon emissions by 2050, nearly everything needs to be electrified. And the electricity comes from alternative renewable sources like solar, tidal, right? Everything needs to be electrified. I think that's fine, right? Think about the devices or anything you use in life. What cannot be electrified? I'm still using a natural gas heater in my home and natural gas stove, but come on, they can be replaced by electricity, right? So basically everything. But there are two industries going to be very hard to electrify. The first one is aviation, which we're going to discuss today, especially for long-range intercontinental airplanes. Now, the other one perhaps is ocean shipping. Okay, so currently those they have diesel engines on these huge ships. To think about everything, everyday use, the things that you use every day. How much of them are actually carried is actually by these ships from overseas? I would say more than 50% or maybe 90%. Okay, a lot of these, the goods, the materials that are carried by these cargo ships from overseas. In fact, for the global trading, 90% are actually through these, basically through the waves, ocean waves. Okay, so that is the second industry. I think it's very hard to decarbonization. But let's get back to aviation. Let me share with you, why I think it's very hard to electrify. Now, I know some of you are aero students and others are humanities students. So I'm going to give you a quiz. Okay, let's imagine there's a Boeing 737 aircraft. Let's say maybe this is a long range, carry 300 passengers. Okay. Now, when the aircraft take off, there's a takeoff weight, right? That takeoff weight includes the weight of the aircraft itself, like frames, engines, controls, avionics, everything, which we call empty weight. Okay. Plus, the fuel, right? You have the fuel tanks. Usually for these long range, we just refuel the whole entire air tank, plus the passengers and their luggages or cargo. Okay. So my question is, what is the percentage of fuel weight to the total aircraft takeoff weight? You have three choices: one 4%, two 40%, three 90%. Which one? 40? Okay, I know that's an aero student. 40%. Okay, so this is significant. To give you an idea, because with anything you fly in the sky, the fuel volume and mass both are important. Mass indicates how much lift will be generated, right? If your fuel, in this case, 44% of the takeoff, 40% of the takeoff weight is actually fuel. That's enormous. And also the volume of the fuel also matters. If you have a huge tank, and it's going to increase aerodynamic drag, okay? So give you some data for Boeing 747-100 aircraft, which is a large, long-range, wide-body airliner carrying about 360 passengers. The takeoff weight is about 735,000 pounds, okay? And the maximum fuel capacity in terms of gallons is about 327,000 pounds, okay? That is equivalent to, 48,445 US gallon, equivalent to 327,000 pounds, okay? So that means 44% of the takeoff weight is for fuel. And maybe another 30% is for the aircraft itself, and then 10 to 15% is for passengers and cargo, okay? So this is very important, okay? The fuel weight and volume. So let me show you what I have here in this figure. This is an energy density comparison between Jet A or liquid carbon fuels, and on the right-hand side, battery, and left-hand side, hydrogen, okay? So you see Jet A is here. Jet A is the reference fuel. So, and then the horizontal axis is relative weight, okay? So basic for the same energy contained in the fuel, what's the weight? And Jet A is reference 1. And then the vertical axis is volume, okay? So again, Jet A is a reference fuel, it's also 1, okay? Now, Jet A is a liquid hydrocarbon fuel, as you can see. It is suited for aviation applications because of the specific energy, both mass and volume based. Now, let's take a look at battery. Let's take a look at battery. So here, this is zinc air battery. I have no idea what that is, okay? I do know a little about lithium ion battery. That's the most popular battery used today. So lithium ion battery, which, let me move this a little bit away so we can see. So this is the point for lithium ion battery, current technology. In terms of relative weight, so that's mass-based energy density, this is about, so this is log 10, 20, 30, 40, 50, 60. So that's 60 times of the weight of Jet A to contain the same energy, okay? So that means you're going to lift 60 times more weight than Jet A, okay? Let's take a look at volume. So volume is about here, maybe this is 40, 50. So again, comparing to Jet A tanks, if you use current lithium ion batteries, the fuel tanks or the battery volume needs to be 40 times bigger. think about how much drag that's going to create. So that's current lithium-ion batteries. But in the future, with technology advancement, we may get to this is 40 times of the weight of Jet A and maybe 12 times the volume. But still, it's not even comparable to Jet A. That's the problem with battery. Okay. One of my former PhD students currently works for Tesla, and he's in charge of all the battery research at Tesla. Before that, he was working for oil company. You see the two industries. And what he told me is that 3 years in the oil company, what he learned is less than 3 months he spent at Tesla. So I'm telling you this story is basic to tell you in battery, Tesla, electrified vehicles, electrified aircraft, the progress is so rapid. Okay, this is really something if you want your career, or especially if you want to become a billionaire, have your own business startup, this is the area to think about. And he also suggests me should buy some Tesla stock, which I did not. That was 2015. Anyway, so we look at battery. The main point is the current battery technology, maybe even in the future with the advancement of battery technology, they're still not same caliber with Jet A. Okay. All right, let's look at hydrogen. Okay, so the two hydrogen, one is liquid hydrogen here, and this is compressed hydrogen at 700 bar. Okay, compressed hydrogen, this is a mature technology. So you can buy compressed to 700 bar the hydrogen tanks today. Okay, so this is straightforward and already in the market. So for compressed hydrogen, that the volume-based energy density, that's about 6 times, let's just say. So that means the volume, the tank to carry compressed hydrogen will be 7 times bigger than the tank for Jet A. Okay, so that's enormous. So that's basically, you're going to have a large aircraft, especially the tanks. For liquid hydrogen better, it's almost 4 times. So, really 4 to 6 times of. Now, if you utilize, this is again, our colleagues in aircraft design, how to use every space inside this wide body, for example, aircraft to store hydrogen, that potentially you can arrange these volumes for hydrogen. Now, the good thing about hydrogen is, they're on the left side from the weight perspective, that for the same weight of hydrogen, either compressed or liquefied, I have about 0.25, 4 times the energy than Jet A. So from the mass perspective, hydrogen wins, right? Hydrogen wins. And then it's the volume that's the challenge, okay? But again, if you look at hydrogen, they're closer to Jet A, more than the batteries, okay? Now the rest, like liquid ammonia, methanol, ethanol, even fat, this is LNG, liquid natural gas. You can put more data points like synthetic fuel, bio-derived fuel, but they are all hydrocarbons. So they're similar in this range, similar to Jet A, small, a little maybe smaller, higher, but similar, okay? So this figure basically gives you an idea how difficult it would be to electrify aircraft. Okay, again, energy density. All right. Okay. All right. So aviation, that's a challenge. We always say, when we don't say difficulties, we always say challenges, because challenges indicates opportunities. So I'm going to talk about what are the research and development opportunities in the aviation industry to achieve zero emission in the future. So, this slide's giving an idea about the decarbonization pathway in the past and also current efforts. Our aero students probably are familiar with these concepts. really the industry are focusing on improved efficiency, right? If I can improve the engine, the efficiency by 10%, that means I'm going to burn 10% less Jet A. I'm going to emit 10% less carbon dioxide, right? I listed a couple of the technologies or approaches. They're not a complete list, but just to give you some flavors about what the aviation, the aerospace industry are doing nowadays. For example, increased bypass ratio, Qiao turbofan, right? Those who have taken 438 air breathing propulsion knows the importance of bypass ratio on the overall efficiency, right? So that's the trend. Higher bypass ratio, higher cycle efficiency, and lower fuel consumption. Now, this is example of Rolls-Royce train family turbofan. They call UltraFan. They claim it's a step change in efficiency. Now, this fan, I mean, besides the fan, there's also a couple of other advanced technologies. But this fan is huge, okay? And then the overall compression ratio by the fan, the compressor is 50, okay? So that's highest ever compression ratio. So again, you understand the importance of compression in jet engines, because that's increase the overall cycle efficiency. Carbon fiber composite material, right? This is to make the aircraft lighter, right? The airframes made of these advanced material instead of titanium or aluminum alloy type material, which are very robust but heavier. So these composite material can potentially reduce the weight of aircraft and therefore enhance the fuel efficiency. Their advanced combustor concept, this is the one that as my colleagues at Zucro are actually working on, called rich burn, quick quench, lean burn combustion. Again, this is to make sure very complete combustion that we don't waste any fuel molecules, right? Every fuel molecule is burned and convert chemical energy to heat, okay? And also reduce other emissions such as NOx, particulate, soot, and so on. There's combined cycle. So again, this is from the cycle perspective to increase efficiency. And finding these super wind designs. This is a very interesting topic. I want to give you two examples. The left one is Lockheed Martin's hybrid wind body, which is supposed to be the future of subsonic air transportation, with fuel efficiency, with low noise and light frame, and all those unique features. And then on the right-hand side is the Boeing truss-braced wing. You probably noticed this aircraft is different from the ones you've taken, right? Look at the wings. It's huge, okay? Very long, thin wings and supported by this diagonal strut, okay, for stability. And this wind design is supposed to reduce drag. And they claim, they expect this kind of design can reduce fuel consumption by 10%, which is huge for current industry, okay? So again, the decarbonization pathway are mainly focused on enhanced efficiency, like from combustion, from aerodynamics, from materials, from the cycle performance. But keep in mind, if these aircraft engines still burn Jet A, no matter, think about how much efficiency you can improve, 10, 20%, that's going to be like breakthrough. This is not enough, okay? So what is the future? If we really truly want to achieve net zero emission by 2050 or 2100, this is the path, what I'm showing you here, okay? This is from IEEE Electrification Magazine. I want to mention that there are mixed views about the future. If you look at, leading experts, even they disagree with each other, okay? I think this is a complex situation. It depends on, maybe each country will have a different approach. depending on what kind of natural resources the country has, what the geopolitical, a lot of considerations. But me personally, I believe this is the future. Okay, if you look at this graph, before 1940s, think about the airplanes, before World War I and II, those propeller airplanes driven by an internal combustion engine burning gasoline, right? So this is gasoline. Those are early aircraft engines. They were slow, but they were significant in terms of their importance to the aviation industry progress. Now, from 50s all the way to today, kerosene, right? Jet A kerosene. Now, in the future, let's say by 2050, okay, it's a kind of like a transition in the next 100 years, transition to eventual zero carbon, okay? Now, in this case, you'll see the yellowish area, that's biofuels, liquid natural gases, synthetic fuels, which we all call sustainable aviation fuels. Sustainable in the sense that their carbon footprint will be significantly less than Jet A, but not zero. Okay, significant less than Jet A. Okay, so this is sort of a transition period for maybe 50 to 60 years. I'm going to talk about synthetic aviation fuels, but again, I want to emphasize this would be a transition because sustainable aviation fuels like biofuels are not exactly zero emission. Okay. Now, what's in the future? So the blue area is battery. Right, it's keep increasing. I mean, it's literally zero right now, but it's going to increase, keep increasing. So by maybe in 100 years from now, you look at the very end of this graph, majority of that is liquid hydrogen, and maybe 10-20% batteries. Okay, that's the future. That is the future for truly zero carbon emissions. Okay. All right. So I'm going to talk about that. But in terms of low emission propulsion technologies, which really is something I've been studying, obviously to a sustainable aviation future, it's going to be multidisciplinary approach. I think this graph on the left-hand side very well gives you an idea, aerodynamic structures, materials, energy, propulsion system, it's all, different disciplines working together. Now, to me, I'm going to talk about low emission propulsion technologies, sustainable aviation fuel, that's the yellow part, and then hydrogen powered propulsion, that's the green part, and eventually last one is battery electric propulsion here. Okay. Now, as I say, because my expertise is propulsion, so I'm going to focus on the propulsion. But as you can see, this is a multidisciplinary approach. I think also very important is optimization of operations aircraft, right? When you design aircraft, optimize it, and also the operations like between airports and routes, all those things. That's also critical. Okay. I once asked a lot of students and friends that are you comfortable to fly on an airplane without a pilot? And many of them said, no, I want to have a pilot just to make me feel safe. But you know what? Research shows that most of the accidents were caused by humans, either pilot or someone on the control tower. Actually, alternatives piloting that's going to happen. It's actually going to be safer, believe it or not. Anyway, the rest of the lecture, I'm going to give you ideas about low emission propulsion technology. Now, the first one we're going to look at is sustainable aviation fuel. Move this to the bottom. So what is sustainable aviation fuel? There are liquid hydrocarbon fuels similar to Jet A, but not exactly the same. Okay, so for example, we know Jet A is a mixture of 300 different species. Okay, it's not a pure chemical species, it's mixed. Sustainable aviation fuels are derived from a variety of feedstocks, including agriculture, forest waste, municipal solid waste, or even non-food crops. Okay, we're going to use thermal and chemical method to convert them to liquid fuels. But again, they are liquid hydrogen carbon fuels, which means because the properties is similar to Jet A, that means there's no need to change the infrastructure, right? The fuel supply, the airport, and even the aircraft itself. Okay, so that's kind of like a short path to solve the problem. In fact, it is the transition step. So on the bottom of this slide, I listed a couple of examples of production of sustainable aviation fuels. The first one is called gas. This is gasification process, fish trough. Okay, the feedstocks like cellulose biomass, like wood, all the agricultural waste, even municipal solid waste. Okay, this liquid fuel can blend with JDA by maximum 50%. Okay. And then this is gasification. This is high pressurized heating process. Now the second is called HEFA, hydroprocessed esters and fatty acids. That's the abbreviation is called HEFA. Again, the feedstock oil crops, cooking oils. And the third one is alcohol to jet. I know a lot of people, colleagues on campus are working on that, alcohol to jet. Again, we have commercial power plants already operating. The feedstocks are corn, sugar cane, cellulose biomass, and this is very an active research area on campus because we're very strong. It is very strong in agriculture and also chemical engineering. The last one is less material. This is called power to liquid. The power basically hydrogen or even including carbon dioxide, and then use like heated metal catalyst to convert these gases from renewable sources to liquid fuel, okay, to liquid fuel like methanol, hydrocarbons, even ammonia. Now, this table also gives you greenhouse reduction potential, and obviously these are optimistic numbers. I know my colleagues in Triple E that on cycle analysis of the feedstock, they might disagree, but overall they could lead to significant reduction of greenhouse emissions. To give you an idea, this is an example biorefinery to generate sustainable aviation fuels. I think I'm going to use the next slide. So basically, we have two ways to do that. The first one is biochemical route, so using microorganisms like bacteria or yeast convert biomass into a liquid fuel. Okay, and then the other one is thermochemical. So basically, use heat, right? Using a gasifier, for example, using heat and often pressurized, because pressurized will help the conversion efficiency to convert biomass into a gas or later to liquid fuel. Okay, I would talk about the hydroprocessed esters and fatty acids. Again, they can be made from renewable feedstock, vegetable oils, animal fats, and even cooking oils. Okay, so these are the different processes to generate liquid sustainable aviation fuel. So what are the challenges and opportunities with sustainable aviation fuel? Well, on the bottom, you see this is Biden's administration's Sustainable Aviation Fuel Grand Challenge. The goal is to scale up. And in 2030, production 3 billion gallons of sustainable aviation fuel, and then 35 billion in 2050, okay? Currently, it's 4.5 million gallons per year. Okay, so as I said, by 2050, this is a transition to the eventual zero carbon emission. that sustainable aviation fuel play a very important role. Now, what are the challenges? Feedstock availability and cost, right? And production capability, infrastructure, refinery, storage tank, transportation system. So basically, there are some power plants, they're smaller scale and on subsidized grants from government, but they're not scaling up yet. Okay. There's also regulatory and certification requirement. In terms of compatibility with existing aircraft, it's like, whatever process generate a liquid hydrocarbon fuel, you cannot just throw that into an aircraft engine. It may cause some problems. The physical properties, the chemical properties, just like boiling point or viscosity, right? And they need to fit into, the current range that works for an aircraft. So that's what we call drop-in fuel approach. So basically, the idea is that we define the fuel, the physical, thermal, and chemical properties, and then go back to the refinery process. You adjust your parameters in those process in order to create a fuel that's going to meet these kind of requirements. Okay. Finally, cost competitiveness, more expensive than conventional jet fuels, yeah, for sure, especially with the scale that we currently have. And also, it competes with other, like agriculture. And I remember, I'm not sure it's inflation or not, but I remember when I first started here, that's 15 years ago, $1 I could buy 10 corns. But today, if you go to Fresh Time, Payless Market, it's almost $1 each, right? So there's a competition with agriculture as well. All right, so that's about sustainable aviation fuels. So I'm going to move on to hydrogen, okay? When I talk about hydrogen, I just, subconsciously feel very excited because it's a magic fuel. As someone whose expertise in combustion science, propulsion, hydrogen is a beautiful fuel to us. Gas is liquefied or cryogenic rockets, and hydrogen is the fuel. Now, the biggest thing is that it only produces water vapor, make it potentially zero emission. So this is why you see, my previous slide, in the future, 100 years from now, the primary hydrogen. Okay. And also compared to Jet A or hydrocarbon fuels, hydrogen produce, very little, nitrogen oxides. Okay, so nitrogen oxides is also a pollution, right? I talked about the third bullet point, from the mass or weight perspective, hydrogen has advantages, right? For the same weight, for 1 kilogram hydrogen versus 1 kilogram Jet A, hydrogen has almost 4 times the energy than Jet A. Okay. And lastly, hydrogen can be used in combustion engines or fuel cells. Both would have high efficiency. Okay. So it depends on, which one. I mean, there's competition between combustion engines or fuel cells. Both utilize hydrogen. We'll see the applications. So I did an interview for the Aerogram magazine from our school. So what I want to really show you here is that hydrogen combustion, I probably can give you 10 lectures on, how hydrogen combusts, but I want to show you, this is a blue flame ball, that's hydrogen combustion. Okay, so if you burn hydrogen, you always see these beautiful blue color. Okay, so that's exactly produced using a colorful high-speed camera from this bomb that behind me. Okay, now I can talk a lot about hydrogen combustion, but I want to point out a few things, especially for those who are not engineering students. Hydrogen is a very, very unique fuel. Okay, it's very light, right? Its molecular weight is like 2. Okay. But light fuel means what? High diffusivity, okay? High diffusion is a very important process in all the chemical propulsion devices, right? Because fuel and air, they need to meet each other to burn. Like they need to get in touch with each other on the molecular level in order to have a chemical reaction. So if hydrogen is highly penetrating, highly diffusive, so the reaction is very fast. Okay, if you look at a hydrogen flame propagation versus Jet hydrogen is 5 to 10 times faster. Okay, and also, hydrogen seems to be a very simple fuel, right? Lightest fuel, but it's the hardest to model. Okay, in our combustion community, why is that? Because it burns very fast, and the molecular weight is so light than air, and there cause instabilities, and so that turbulent combustion is very hard to predict. Okay, so hydrogen, as you can see, has a lot of advantages, but also challenges that we have to deal with. Now, I know many of you would ask, you immediately ask the question, where do we get hydrogen? And I wish I had the answer, but here, hydrogen production. This is a graph that I took from Department of Energy, our website. This basically summarizes sustainable pathway to hydrogen. So as you can see, there are multiple ways to generate hydrogen. The first obvious is electrolysis, right? Splitting water into hydrogen, oxygen using electricity from renewable sources, right? And you separate hydrogen and oxygen. And the second method is biomass conversion, either biochemical or thermochemical, and then, separate it, reform to hydrogen, or using the yeast or bacteria techniques to produce hydrogen. Okay, the last is on the right-hand side, photosynthesis, like solar conversion, thermolysis, basically using thermal generated heat to produce hydrogen, or photolysis. Okay, now in terms of technology matureness, this is from the left, this is more mature, and the right-hand side is more in the development. Okay, but that's the path of hydrogen. Sometimes you hear the word green hydrogen. Okay, basically that's from electrolysis from renewable electricity. Okay. One of my colleagues told me that he did psychoanalysis of a hydrogen-powered aircraft, and he said, this is not more economic than Jet A. Sure, because hydrogen is a lot more expensive nowadays. But the good news is that if you look at this figure, it's to the top. If you look at this figure, this is predicted by Williamson, the price, the cost. This is in Europe. The cost USD dollars per kilogram synthetic fuels. So those are biofuels, for example, sustainable fuels. And this is liquid hydrogen. Okay. So currently there are about $400 per kilogram. And then for liquid hydrogen, $250 per kilogram. It's pretty high, okay, comparing to Jet A. But with technology advancement, this is synthetic fuel here. By 2050, it's over here, 200 and 150. And for liquid hydrogen, it's about 50, okay? So there is a future. Okay. All right. Now, okay. Hydrogen, I know this kind of block on view. Hydrogen-powered aircraft engine, they're not like in the future. That's happening right now. So if you search news hydrogen aircraft turbofan, you'll see nearly every major engine manufacturers like GE, General Electric, Rolls-Royce, CMF International, Honeywell, they're all investing in hydrogen-powered turbofan engines. Okay, so this is an example. This is, I believe, just a couple months ago in the news. Yes, November 29th, 2022. Okay, Rolls-Royce announced with their partner EasyJet that they successfully tested a hydrogen jet engine on ground. This is a AE 2100A regional aircraft engine. Okay, now this is a turbofan engine powered by hydrogen. So as I said, all the major engine manufacturers are testing hydrogen-powered turbofan. Okay. Now another very exciting sector is smaller aircraft. For example, you see this news, hydrogen-powered aviation reaches milestone with zero AVWAS flight. So this is a small startup company. And this is a 19-seat hydrogen electric prototype airplane, which I believe flew maybe 10 minutes, 20 minutes, which the company claimed is a historic event, which probably was. So this is a hybrid. So basically for this prototype, the two engines, right? One is still the turboprop engine burning jet A, because all the testing and you want to make sure that at least one of the engines is the reliable engine, that old one. And then the second one, the other one is running on hydrogen fuel cell. Okay. On the bottom left, this is a Dash 8 commuter plane, flew for 15 minutes with hydrogen fuel cell. This is from this company called Universal Hydrogen. Okay, so again, it has two engines. One of them converted to a hydrogen fuel cell and carried about 60 to 70 pounds of hydrogen. Okay, so the basically modified engine that flew for 15 minutes. So the key idea, whether it's hydrogen combustion engine for larger aircraft or hydrogen fuel cell for relatively smaller aircraft, they're taking place. Okay. Okay. So what are the challenges and opportunities for hydrogen? So I list a couple of them, but I think the first one is the biggest challenge, which is low energy density by volume. Okay. Perhaps for smaller aircraft over short distance, like 100 miles, 200 miles, commuter aircraft, compressed to hydrogen, compressed to 800 bar. I'm sorry, that's not PSI, that's too low. Bar, should 800 bar, that probably can do the job. But larger aircraft, from the energy comparison that I showed you earlier, they must be liquefied. Okay. So, to liquefied hydrogen, hydrogen needs to be stored at 253 negative Celsius. Okay, so that's what we call cryogenic propellant or fuel. Okay, there are other ways to store hydrogen through advanced materials, but cryogenic is one of the ways. So if that's the case, they needs to be extremely well insulated. And also venting, just like the rockets. You see sometimes when the space shuttle launching, you see those like a white smoke. That's because the cryogenic liquid hydrogen and the cryogenic liquid oxygen, they need to be vented to prevent the tank from exploding. Okay, so that's, I think, liquid hydrogen or hydrogen storage. That's the biggest barrier for deploying hydrogen technology in aircraft. Okay, and lastly, hydrogen tanks. Hydrogen molecular weight is too. It's very diffusive. Okay, if you have tiny cracks or gaps, hydrogen just gave away. Okay, there's no way you can correct that. And also, some metals exposed to hydrogen will become brittle. Brittle is like, it's, and how to describe brittle, just basically the material will fail, right? So I think that low energy density of hydrogen, that's the biggest barrier. However, as someone coming from the propulsion background, just like liquefied hydrogen, cryogenic hydrogen, this is not a new technology. 50 years ago, we sent rockets to space that used cryogenic. It's just that we need time and also scaling to solve the problems. Okay. Another limitation is high cost. As you can imagine, there's so much more expensive than Jet A. Safety. This is hydrogen is so reactive, highly flammable, right? So for every fuel there's a flammability limit. and hydrogen has the widest limit. If this room has from 4% to 96% by volume, hydrogen, it has a chance to explode. Okay, so it's very wide flammability. But for methane or propane, that their range is so much narrower. Okay, so hydrogen is quite dangerous. Because we have multiple detectors in the lab when we're dealing with hydrogen, just to see if there's any leakage. Okay. All right. So I have about 20 minutes. I'm going to talk about electrified aircraft propulsion. So this is the third, as you can see, in 100 years also, electrified aircraft will, take a significant portion of the whole industry. What are the advantages of electrified aircraft? And obviously, that's the environmental impact, net zero, right? Now, I'm telling you, the most exciting business sector of aviation that is going to use electrified propulsion is advanced air mobility. You probably heard about that. Those are the 2 seats or 4 seats passage vertical takeoff or landing aircraft that are going to transport you from here to Indianapolis or to Chicago. Okay, so that's advanced air mobility. It's kind of provides you a affordable, efficient way for urban transportation. Okay. Now, in fact, in the aerospace industry, if you ask our students what are the most exciting fields, they'll tell you one is rockets, like I want to work for SpaceX, I want to work for Blue Origin. And then the other sector is advanced air mobility. I mean, you're going to see a lot of startups and billionaires, maybe from Peru, in that sector. Lastly, enables small short-range aircraft with high level of autonomous operation. I talk about autonomous. That's completely is going to happening in the next few decades. So I have an example with here, NASA X-57 Maxwell airplane. This is a NASA's like an all-electric demonstrator. They have 14 motors all across the wings. Generate 240 kilowatts, okay, all distributed electric power, high efficiency cruise propellers at the wings, okay. They named it Maxwell is in honor of James Maxwell, who pioneered the electromagnetism theory. Anyway, so this is the all-electric first aircraft that NASA is testing. Now, on the right-hand side, you see this picture. This is Pipistrel Taurus electric 2-seat aircraft, all electric. Okay, this is on sale. If you have enough money, you can buy one today. Okay. The range for these two are, typically like 50 to 100 miles. All right, so there are 3 types of electrified aircraft. The first is all turboelectric or partially turboelectric, in the sense that you still have the traditional either turbo shaft, the turbo fin engine burning jet A, you see this fuel, but they're going to drive a generator. Okay, so that is the power source, generator. And then the electric bag either to generate, through these motors to generate propellers. Okay. The partially, again, that both the fans, kind of like the split between these distributed propellers and the fin in terms of thrust. This is a hybrid, which means I have turbo engine driven generator for electricity plus battery. Okay. Now, a lot of work going on for this hybrid motion, the configuration is really determining the ratio between the two, right? How much battery you want, how much from the turbo. And the last one is all electric. So all the energy power source come from the battery. Now, again, we're going back to energy density because that's really key for anything fly in the sky. So this is shows battery compatibility required for all electric urban mobility aircraft. So again, these are the small aircraft for advanced urban mobility. So again, you can see this is battery specific energy in terms of mass per kilogram. And this is a range in terms of miles. So, 150 for 2 to 3 passages in the 50 miles is completely achievable by battery. Okay. Now on this side, it's a little bit challenged, but still is a solvable problem, right? Require 300 to 400 watts hour per kilogram, and for 2 to 4 passages, 120 miles range. Okay, so these should all be able to do electrified, given the advance in battery, even though the current technology is only state-of-art lithium ion battery is only 170 watts hour per kilogram. So again, you see from here, this is Tesla model, this is the energy density, about 130, something like that. And this is Nissan, and there are other types of battery technologies, but all of them, it's going to be very hard to exceed 500 watts hour per kilogram. Okay, so the question is, will battery eventually advance to the point that we can do electrified aircraft for medium long range? Okay, so there's a study that I cited over here. Basically for regional aircraft, the specific energy required is about 600 watts hour per kilogram. And then for these narrow body, larger aircraft, it's about 800. And then for these wide body, intercontinental aircraft, it's 14, 13 watts hour per kilogram. Okay, so these, in fact, battery technology may be advanced to 500, but still below all from regional to narrow body to wide body aircraft. Okay, so this is a challenging problem over here. So this table gives you a better idea that for commuter, regional aircraft, electric or hydrogen fuel cell would be good choice. But for short haul, medium haul, hydrogen or synthetic sustainable aviation fuel, and long haul, it must have the energy density similar to JET, liquid hydrocarbon fuel. Okay, so this is by 2050. Now, if you want to extend that to 2100, this column, you're going to have more and more orange color, which is hydrogen. Okay, so again, because of the energy density. So this is my last slide. What are the opportunities and challenges for electrified aircraft propulsion? I have to say, this is a very exciting field. Whenever people talk about sustainable aviation, electrified aircraft, that's the first word that comes to their mind, right? So this is especially in the emerging market of advanced air mobility and commuter applications. So this is a smaller aircraft, definitely electrified aircraft. It's already taking place. Regional short haul, maybe a mix of electric and hydrogen fuel cell, but medium and long haul likely rely on hydrogen and sustainable aviation fuels. Okay. Now, this sector highly depends on battery technology advancement, packaging, chemistry, and so on. But one thing I want to point out is that most battery research so far have been for what? For ground applications like electric cars, right? Very few, battery are designed for aircraft. Think about aircraft, you can fly at, up sky 10,000 feet or even higher. It's cold there, okay? These electrochemistry highly depend on what? Temperature, okay? And also the electric circuit. So basically, I think that even for advanced air mobility and regional short haul, these smaller aircraft, battery research is just starting because they won't be very different from ground applications. Lastly, I think FAA and NASA working together, we need more demonstrations, more certifications to sort of promote the growth of electrified aircraft market. Okay, I think that's my last slide. I'll stop over here. We do have a bit time, and I'm happy to answer your question. Yes.
So there's sort of some talk about like past the point of no return as far as carbon emission goes. Like it's just planned to like 2050. Is that's like well within the point of no return sort of thing as far as like we can stop the changes that we're causing?
Yeah, I think some scientists believe we have passed, unfortunately, we have passed that. I don't know about it. I cannot give you, but there's a famous saying, the best time to plant a tree is 10 years ago or now. So I think that all these, what I've talked about needs to be happening quickly. Yeah.
So do you think 2050 is like soon enough, or is that like the most reasonable time frame that we can?
Okay, I think for aviation, 2050 is a reasonable one because it's the hardest sector to come on. But the others like electrical cars, that can happen more quickly than it is now, right? It's Tesla cars, and hydrogen fuel cell cars by Toyota, Honda, they're running on roads. Yeah, it's just like, you need to give a little bit economic return or incentive to get those, but also you need to create the infrastructures for, green, for renewable electricity and green hydrogen. Yeah, so those transportation sectors can happen more quickly. But aviation is more difficult. The main reason is the energy density that have been emphasized. Yeah. Yes.
I think you mentioned there's like a limit of like 500 watt hours per kilogram.
Mhm.
Is there like something that's like a physical barrier that's like there, or is that
Good question. I asked it because I'm not a battery person, so I asked quite a few batteries experts, researchers. They're saying that for lithium ion batteries, like 400 is kind of the limit. I think it's the physical and chemical barrier. However, if you choose more advanced material, with different chemistries, exotic chemistry materials, that can be increased. However, I asked, is there anything, just in theory, any material, any chemistry that can create a battery that has similar energy density as Jet A? The answer is no. At least in the next few decades, we don't see that. Okay. Maybe they can reach to 600, 800, maybe 1,000, but harder beyond that. Yes.
Go on.
Okay.
So you said, or you had a slide that was about the price per kilogram, I think, different fuel mixes.
Mm-hmm.
And I was just curious, like with that, I think the bottom line is kerosene. If I'm reading that right. Basically with the hydrogen or biofuel, because they have higher energy density per gas, would those actually be more cost effective at those like future points?
I think it's more about the resources. For example, for sustainable aviation fuel, the liquid hydrocarbon fuel, the feedstock availability, and of the process itself. But nevertheless, if you produce those in larger scales, the cost will go down. I mean, a lot of those startups, they just produce like 1,000 tons of fuel. I mean, they broke. Because this, those are so expensive if you produce just a small amount. So from that perspective, yeah. Yes.
Referring to the same graph, Professor, do you think so? I'm not touching upon the experimental tools. I'm talking specifically about the kerosene.
Mhm.
Do you think that excuse my non-scientific, bang for buck percentage will increase for the biofuels, given the fact that the kerosene might skyrocket in price at any point in time? Because this graph kind of supposes that the kerosene will be staying
Okay.
the same price.
Right. I think that's a good question. This is kerosene. I suppose the scientists who produced this did not consider any geopolitical conflicts because kerosene price fluctuate a lot with that, right? And just a few months ago or 2 years ago with, Saudi Arabia, they decide to reduce their production, your price goes up. But this is not necessarily the actual cost for cash. Okay, so this is highly dependent on geopolitics. Yeah. Yes.
Kind of a question that's probably mostly because of my ignorance on glycolysis.
Okay.
With glycolysis, are you able to do it on any sort of water, or does it need to be pure in order to split?
For water electrolysis?
Yeah.
I would say it needs to be pure. I'm not an expert on that, but based on my knowledge, because for water electrolysis, you have the two electrodes that was made of special materials. It could poison the electrodes or just affect this electric surface chemistry. Usually needs to be demineralized water. Maybe you have something to add.
Yeah, so we do have some that are half cells that are for offshore wind that take the natural seawater. So that is the chemistry development, of course, avoiding to have to do the traditional.
Excellent. Very good.
Something seems to be wrong with the price here. I don't understand.
Okay. Is it, it's per kilogram? That seems too high, isn't it?
Yeah.
Yeah, okay, I'll double check the reference. Cost projection, is that because it's in Europe?
No. My guess is that it's the infrastructural cost as well, as opposed to production cost. So what is the infrastructure at the aviation versus, the other? So it's not just the fuel,
Mhm.
it's also.
Oh, the infrastructure, could be, yes. Very good point. Other question? Yes.
One more. So with kind of the sustainable aviation fuel, those co-valorization, or whatever, of CO2, the carbon dioxide and hydrogen, it's kind of reducing the carbon dioxide. I was wondering, is that something that you could in flight, just carry your hydrogen and then essentially produce your sustainable aviation fuel and essentially turn
onboard factory.
it's zero overall factor, stealing the carbon dioxide from the atmosphere and using it as fuel, or is there
I'm sure there are research going on, or maybe even startups on that. And I even heard a story that there's an onboard carbon capture device. Like you burn jet fuel, right? The generate carbon dioxide immediately being captured, and then when airplane landed, well, let's just take the capture the CO2. I think those are being investigated, but I have not seen larger scale, very promising applications. Yeah. But you never know. Any other question? Yes.
Sorry. On the hydrogen slide, I think might have been a little bit later. There was something about production of nitrogen oxides.
Yeah.
Like hydrogen fuels. I was wondering, how does hydrogen combustion produce any sort of nitrogen oxides? Or is it just
That's because the nitrogen the nitrogen atom in nitrogen oxide come from entering air. That chemistry. Yeah. Other questions? Okay, if not, well, thank you for coming today. I enjoyed